Section 11.3, breaking down the process subproblem. We'll name our overall process function process data. It will take the mystery book file name and the name of a directory of known author books as parameters and return the name of the closest known signature. Looking at our description for the process step, it seems that we have three subproblems to solve here. Figure out the signature for the mystery book. That's our unknown signature. We'll name this function makeSignature. Figure out the signature for each of the books whose author we know. These are our known signatures. We'll name this function getAllSignatures. Compare the unknown signature to each known signature to figure out which known signature is closest. Because close signatures will have small differences, we'll name this function lowestScore. We'll work on our top-down design for each of these subproblems in turn. Figure 11.1 shows a diagram of what we have so far.
Figure 11.1. Functions diagram with the three subtasks of process data.
Section 11.3.1. Figuring out the signature for the mystery book. The function for this task, makeSignature, will take the text for our book as a parameter and return the book's signature. At this point, we need to decide on the features that we'll use to determine the signature for each book. Let's break this down by thinking back to the previous example passages. We noticed there are differences in the author's passages based on the complexity and length of sentences. You may have also suspected that the authors may differ in the length of words used and ways they use words. For example, some authors may be more repetitive than others. As such, we'll want some features to be based on the structure of the author's sentences, and we'll want others based on the words that the author uses. We'll look at each of these in detail. Features related to the structure of the author's sentences. In our earlier Doyle versus Dickens example, we talked about using the average number of words per sentence as one feature. We can calculate this by dividing the total number of words by the total number of sentences. For example, consider the following text. The same day there arrived through the post a small cardboard box addressed to me, which I found to contain a very large and lustrous pearl. No word of writing was enclosed. If you count the words in sentences, you should find that there are 32 words. Cardboard counts as one word. And 2 sentences. So we'll calculate the average words per sentence as 32 divided by 2 equals 16. This will be the average number of words per sentence feature. We also notice that the complexity of sentences may vary between authors. That is, some authors have sentences with many more commas and semicolons compared to other authors. So it makes sense to use that as another feature. More complex sentences have more phrases, which are coherent pieces of sentences. Breaking a sentence into its component phrases is a tough challenge in its own right. And although we could try to do it more accurately, we'll settle here for a simpler rule of thumb. Namely, we'll say that a phrase is separated from other phrases in the sentence by a comma, semicolon, or colon. Looking at the previous text again, we find that there are 3 phrases. The first sentence has 2 phrases. The same day there arrived through the post a small cardboard box addressed to me, and which I found to contain a very large and lustrous pearl. The second sentence has no commas, semicolons, or colons, so it has only one phrase. As there are 3 phrases and 2 sentences, we'd say that the sentence complexity for this text is 3 divided by 2 equals 1.5. This will be the average sentence complexity feature. We hope that these sentence-level features intuitively make sense as things we could use to differentiate how authors write. Next, let's start looking at the ways that authors may differ in their use of words. Features related to the author's word selection. You can probably think of your own metrics for word-level features, but we'll use 3 here that in our experience work well. First, it's likely that some authors use shorter words on average than other authors. To that end, we'll use the average word length, which is just the average number of letters per word. Let's consider this sample text that we created. A pearl, lustrous pearl, rare, what a nice find. If you count the letters in words, you should find that there are 41 letters and 10 words. Don't count punctuation as letters here. So, we'll calculate the average word length as 41 divided by 10 equals 4.1. This will be the average word length feature. Second, it may be that some authors use words more repetitively than others. To capture this, we'll take the number of different words that the author uses and divide it by the total number of words. For our previous sample text, there are only 7 different words used. A, pearl, lustrous, rare, what, nice, and find. There are 10 words in all, so our calculation for this metric would be 7 divided by 10 equals 0.7. This will be the different words divided by total words feature. Third, it may be that some authors tend to use many words a single time, whereas other authors tend to use words multiple times. To calculate this one, we'll take the number of words used exactly once and divide it by the total number of words. For our sample text, there are 5 words that are used exactly once: lustrous, rare, what, nice, and find. There are 10 words in all, so our calculation for this metric would be 5 divided by 10 equals 0.5. This will be the number of words used exactly once divided by total words feature. In all, we have 5 features that will make up each signature. We'll need to store those numbers together in a single value, so we'll end up using a list of 5 numbers for each signature. Let's dig into how we'll implement each of these features, starting with the word level ones and proceeding to the sentence level ones. We'll go in this order. Average word length. Different words divided by total words. Words used exactly once divided by total words. Average number of words per sentence. Average sentence complexity. For each one, we'll ultimately end up writing a function. We have an updated diagram with function names for each of these 5 new functions that will help us implement make signature in figure 11.2. Do we need to further break down these problems, or are they okay as is? Let's see.
Figure 11.2. Functions diagram with the additional 5 subtasks of make signature.
Average word length. The function for this task, average word length, will take the text of the book as a parameter and return the average word length. We might start solving this task by using the split method on the text. As a reminder, the split method is used to split a string into a list of its pieces. By default, split will split around spaces. The book text is a string, and if we split around spaces, we'll get its words. That's exactly what we need here. We can then loop through that list of words, counting up the number of letters and number of words. That's a good start, but we need to be a little more careful here because we don't want to end up counting non-letters as letters. For example, pearl has 5 letters, but so does pearl, with period or pearl, with exclamation marks or pearl in parentheses. Aha! This sounds like a subtask to us. Namely, we can divide out the subtask of cleaning up a word into its own function to be used by average word length. We'll call that cleanup function cleanword. There's another benefit to having our cleanword function, and that's to help us identify when a word is actually not a word. For example, suppose one of our words in the text is 3 dots. When we pass this to cleanword, we'll get an empty string back. That signifies that this in fact isn't a word at all, so we won't count it as such. Different words divided by total words. The function for this task, different to total, will take the text of the book as a parameter, and will return the number of different words used divided by the total number of words. As with average word length, we need to be careful to count only letters, not punctuation. But wait, we just talked about a clean word function that we needed for average word length. We can use that function here as well. In fact, we'll use clean word in most of our 5 feature tasks. This is the sign of a useful, general-purpose function. Our top-down design is going well. We can see how the clean word function will be called by both functions in our updated function diagram in figure 11.3.
Figure 11.3. Functions diagram with 2 functions, both using our clean word function to help.
There's one extra complication here, though, and it involves words like lowercase pearl, pearl, capital P, and uppercase pearl. We want to consider those to be the same words, but if we simply use string comparisons, they will be treated as different words. One solution here is to split this off into another subproblem to convert a string to all lowercase. We could also think of this as another part of cleaning up a word, right along with removing the punctuation. We'll go with this second option. What we'll do then is make our clean word function not only remove punctuation, but also convert the word to lowercase. You might wonder whether we need to split off another subtask here, one that determines the number of different words. You could do that, and it wouldn't be a mistake to do so. However, if we persevere without doing that, we'll see that the function remains quite manageable without this additional subtask. Practice and experience over time will help you anticipate when a task needs to be further broken down. Words used exactly once divided by total words. The function for this task, exactly once to total, will take the text of the book as a parameter and will return the number of words used exactly once divided by the total number of words. We're going to need our clean word function here as well for reasons similar to why we needed it in the prior 2 tasks, to make sure we're working only with letters, not punctuation. Again, while we could split out a subtask to determine the number of words that are used exactly once, we'll find that it doesn't take much Python code to do this. So we'll just leave this task alone without splitting it further. Average number of words per sentence. The function for this task, average sentence length, will take the text of the book as a parameter and will return the average number of words per sentence. To split our text into words for the previous 3 tasks, we can use the string split method. How do we split our text into sentences? Is there a string method for that? Unfortunately, there isn't. For that reason, it will be helpful to split out a task to break our text string into sentences. We'll call the function for that subtask getSentences. The getSentences function will take the text of the book as a parameter and will return a list of sentences from the text. What's a sentence? We'll define a sentence as text that is separated by a period, question mark, or exclamation point. This rule, while convenient and simple, is going to make mistakes. For example, how many sentences are in this text? I had at that time just entered the family of Mrs. Cecil Forrester in the capacity of governess. The answer is 1. Our program, though, is going to pull out 2 sentences, not 1. It'll get tricked by the word Mrs., which has a period at the end. If you continue with authorship identification past this chapter, you could work on making your rules more robust, or use sophisticated natural language processing, NLP, software to do even better. For our purposes, however, we'll be content with this rule that sometimes gets sentences wrong because most of the time we'll get them right. If we're only wrong once in a while, the errors won't have an appreciable effect on our metric. Average sentence complexity. We'll name the function for this task average sentence complexity. It will take the text of a sentence as a parameter and return a measure of the sentence complexity. As we discussed previously, we're interested in quantifying sentence complexity using the number of phrases in a sentence. Much as we used punctuation to separate sentences from each other, we'll use different punctuation to separate phrases from each other. Namely, we'll say that a phrase is separated by a comma, semicolon, or colon. It would be nice to have a subtask to break a sentence into its phrases, just like we had a subtask to break text into its sentences. Let's make that happen. We'll call the function for that subtask getPhrases. The getPhrases function will take a sentence of the book as a parameter and return a list of phrases from the sentence. Let's pause for a moment and think about what we're doing with our getSentences and getPhrases functions. They're both quite similar, come to think of it. All that distinguishes them is the characters that they use to make the splits. GetSentences cares about periods, question marks, and exclamation points, whereas getPhrases cares about commas, semicolons, and colons. We see an opportunity for a parent task that would simplify both of these tasks. Namely, imagine that we had a split-string function that took 2 parameters, the text and a string of separator characters, and it returned a list of pieces of text separated by any of the separators. We could then call it with period, question mark, exclamation mark to split into sentences and comma, semicolon, colon to split into phrases. That would make both getSentences and getPhrases easier to implement and reduce code duplication. This is a win. At this point, we've fully fleshed out the functions necessary to support the higher-level function makeSignature, as reflected in Figure 11.4. We'll next turn to the getAllSignatures function.
Figure 11.4. Functions diagram with all the supporting functions for the makeSignature function complete.
Figuring out each known signature. We just worked hard to break down our makeSignature function into 5 main tasks, 1 for each feature of our signatures. We designed that function to determine the unknown signature, the signature for the mystery text whose author we're trying to identify. Our next task is to figure out the signature for each of the books for which we know the author. In the resources for this book, under the CH11 folder, you'll find a directory called Known Authors. In there, you'll find several files, each named as an author. Each file contains a book written by that author. For example, if you open Arthur_Conan_Doyle.txt, you'll find the text of the book, A Study in Scarlet by Arthur Conan Doyle. We need to determine the signature for each of these files. Amazingly, we have far less work to do to solve this problem than it may seem. That's because we can use that same makeSignature function, the one we designed to determine the signature of the mystery book, to also determine the signature for any known book. We'll name the function for this task getAllSignatures. It wouldn't make sense for this function to take the text of one book as a parameter because it's supposed to be able to get the signature for all of our known books. Rather, it will take a directory of known books as a parameter. Its behavior will be to loop through the files in that directory, calculating the signature for each one. We need the function to tell us which signature goes with which book. In other words, we need it to associate each book with its corresponding signature. This kind of association is precisely why Python has dictionaries. We'll therefore have this function return a dictionary, where the keys are names of files, and the values are the corresponding signature. Our function diagram didn't need any new functions to support the getAllSignatures function, so our updated diagram in figure 11.5 just shows how getAllSignatures calls makeSignature.
Figure 11.5. Functions diagram updated for getAllSignatures to call makeSignature.
Finding closest known signature. Let's recap what we've designed so far. We've designed our makeSignature function to get us the unknown signature for the mystery book. We've designed our getAllSignatures function to get us all of our known signatures. Now, we need to design a function that tells us which of those known signatures is best, that is, which known signature is closest to our unknown signature. Each of our signatures will be a list of 5 numbers giving the quantity for each of our 5 features. The order of these numbers will be the same order we used before. Average word length, different words divided by total words, words used exactly once divided by total words, average number of words per sentence, and average sentence complexity. Suppose that we have 2 signatures. The first one is 4.6, 0.1, 0.05, 10, 2, which means that the average word length for that book is 4.6. The different words divided by total words is 0.1, and so on. The second signature is 4.3, 0.1, 0.04, 16, 4. There are many ways to get an overall score giving the difference between signatures. The one we'll use will give us a different score for each feature, and then we'll add up those scores to get our overall score. Let's look at the values of each signature for the first feature, 4.6 and 4.3. If we subtract those, we get a difference of 4.6 minus 4.3 equals 0.3. We could use 0.3 as our answer for this feature, but it turns out to work better if we weight each difference using a different weight. Each weight gives the importance of that feature. We'll use some weights, 11, 33, 50, 0.4, 4, that in our experience have proven to work well. You might wonder where the heck these weights come from, but note that there's no magic about them. In working with our students over the years, we've just found that these weights seem to work out. This would be only a starting point for a stronger authorship identification program. When doing this type of research, people routinely tune their training, which means to adjust weights to obtain stronger results. When we say that we're using weights of 11, 33, 50, 0.44, it means that we'll multiply the difference on the first feature by 11, the difference on the second feature by 33, and so on. So, rather than getting a difference of 0.3 for the first feature, we'll get 0.3 times 11 equals 3.3. We need to be careful with features like the fourth one, where the difference is negative. We don't want to start with 10 minus 16 equals minus 6 because that's a negative number, and that would undo some of the positive difference from other features. Instead, we need to first make this number positive, and then multiply it by its weight. Removing the negative sign from a number is known as taking the absolute value, and the absolute value is denoted as abs. The full calculation for this fourth feature, then, is absolute value of 10 minus 16 times 0.4 equals 2.4. Table 11.1 gives the calculation for each feature. If we add up all 5 scores, we get an overall score of 14.2.
Table 11.1. Calculating the difference between 2 signatures.
Remember where we are in the top-down design. We need a function that tells us which known signature is best. Well, now we know how to compare 2 signatures and get the score for that comparison. We'll want to make that comparison between the unknown signature and each known signature to determine which known signature is best. The lower the score, the closer the signatures. The higher the score, the more different the signatures are. As such, we'll want to ultimately choose the signature with the lowest comparison score. We'll name the function for this task lowest score. It will take 3 parameters: a dictionary mapping author names to their known signatures, an unknown signature, and a list of weights. The function will return the signature that has the lowest comparison score with our unknown signature. Think about the work that this function will need to do. It needs to loop through the known signatures. We can do that with a for loop. No need for a subtask there. It will need to compare the unknown signature to the current known signature. Oh, that's a subtask right there, embodying the scoring mechanism that we outlined in Table 11.1. We'll name the function for that subtask getScore. Our getScore function will take two signatures to compare and the list of weights and return the score for the comparison between these two signatures.